There's this incredible magic to finding a hidden pattern, especially one buried in a string of numbers that just seems totally random. Today, we're going to crack a particularly tricky code using a tool that's surprisingly simple but incredibly powerful. So let's jump right in. We've all seen sequences like this one, right? The famous Fibonacci sequence, where you just add the two previous numbers to get the next one. It's a classic for a reason. The pattern is sitting right there on the surface. Okay, that's the easy stuff. But what happens when the pattern isn't so obvious? What if you're staring at a sequence that looks like it has no logic at all? Where would you even begin to find the next number? Take a look at this. 1, 2, 4, 8, 16. And you're thinking, okay, 32, obviously, right? Wrong. The next number is 31. What? And then 57. The simple pattern just, poof, vanishes. This is a famously tricky sequence, and today we're going to solve it together. So our challenge is set. How in the world do we tackle something like this without just, guessing? Well, it turns out there's actually a system. The tool we're going to use is called Conway's differencing. Now, the name might sound a little formal, but the idea is just beautiful in its simplicity. We're going to find the difference between terms over and over again, building this sort of pyramid of numbers that's going to reveal the hidden logic buried deep underneath. All right, enough talk. Let's put this thing into action. Time to start digging and see what we can find. The whole thing is basically just two simple steps. Seriously. First, we go down by subtracting. Then, once we hit bottom, we go back up by adding. That's the whole game. Let's see it in action. Okay, here we go. First layer, we're just going to subtract each number from the one right after it. So 2 minus 1, that's 1. 4 minus 2, that's 2. 8 minus 4 is 4. And we just keep doing that all the way across. And just like that, we've got our second row. And now, well, we just do the exact same thing again. We take that new row we just made and apply the same logic. 2 minus 1 is 1. 4 minus 2 is 2. See? We're just systematically digging down one layer at a time. Okay, let's go one more time. We apply the rule again, and look at that. Our fourth row is 1, 2, 3, 4, 5, 6. Now that is a pattern I think we can all get behind. We are getting super close. And bam, there it is, the big reveal. One more layer down, and we hit bedrock. It's a constant, steady row of ones. This is it. This is the key we've been looking for. It's like finding the hidden engine that's been driving this whole crazy sequence from the start. Okay, so we found our foundation. Believe it or not, the hard part is over. Now all we have to do is reverse the process. Just build our way back to the top, and the missing numbers are going to pop right out. So first, we extend that foundation out. We just pop another 1 on the end. And now, instead of subtracting, we add up. See that 6 in the row above? We add our new 1 to it, and we get 7. And boom, we found our first new piece of the puzzle. And the logic just keeps flowing up. That new 7 we just found, we add it to the 22 in the row right above it, and that gives us 29. You can really see how we're filling in the gaps now, right? And we keep on rolling. That 29 we just got gets added to the 64 above it, which gives us 93. We are so close. You can see those empty spots on the top row are just waiting to be filled in. And there it is. By just continuing that simple addition all the way back to the top, we've got our solution. The next numbers in that sequence that looked so impossible, 256, 386, and 562. The code is officially cracked. So that was pretty cool, right? We found a row of ones, but what's really amazing about this method is that it's way more flexible than you might think. The foundation isn't always going to be that simple. For instance, take the sequence of perfect cubes, 0, 1, 8, 27, and so on. If you do the exact same differencing method here, you find something different. You bottom out at a constant row of 6s. The process is the same, but the bedrock is different. And get this, sometimes the foundation isn't even a single number. For this sequence here, you go all the way down and you find this steady repeating rhythm, 2, 1, 2, 1. And that's totally fine. As long as the pattern is predictable, you can use it to build your way back up. But, all this success raises a really important question. Is this thing a magic key? Does it unlock every single sequence out there? Let's find out. So, what do you think? Is this differencing approach totally foolproof? Can we just throw any sequence at it and expect an answer? And the answer, maybe surprisingly, is a big no. And knowing this is just as important as knowing when it does work. Just look what happens when we try it on something as simple as the powers of 2. The difference is, well, they just repeat the original sequence over and over and over. You never hit a stable foundation. You're just stuck in an infinite loop. So what's the big idea here? What's the takeaway? This method, it's so much more than just a clever party trick. It's a really powerful tool for thinking. So why does this all matter? Well, first, it's got what you'd call a low floor and a high ceiling. I mean, anyone can start with basic subtraction, right? But it leads you to some really deep mathematical ideas. Second, it kind of reduces your cognitive load. It takes this abstract, tricky problem and turns it into something visual, something you could almost build with your hands. And finally, and this is the really cool part, this is basically a stepping stone to calculus. That first row of differences we found, you can think of that as the sequence's velocity. The second row, that's its acceleration. You're literally visualizing rates of change, which is the heart and soul of calculus. So I'll leave you with this question to chew on. What's actually the more powerful tool? One that works every single time, no questions asked, or one that teaches you its own limits? Because, knowing when a tool fails, that forces us to ask why this problem is different. And that, well, that's where the real learning always begins.